Good morning, students. Now we'll move on to the lecture on local replication technologies. What are the technologies used for local replication, to locally replicate the data? In the last class, we have seen how consistency of a replicated database can be maintained. That can be maintained by treating a transaction having some 4 IO operations as a single transaction, and based on execution of those 3 input output operations on a transaction, they should be immediately returned to the source where the original copy is being maintained. Now, once they are written to the source, they should be in the same order written to the target where the replica copy is being taken. Right? So once all are written in the same order in which they are saved on the source, then we can say that the data is preserved consistently on the replicated copy also. But if 1, 2 IO operations out of the transaction are not written, and before that 3rd and 4th IO operations are written onto the replica copy, then we can't have any proof of what has been updated in IO operations 1 and 2. So this will create inconsistent copy of the data on the replica or the target where the replicated copy is stored. One second, I'll just change my pen battery. Okay, sorry for the interruption. Okay, this is how we ensure consistency of the replicated database on a target device. Target device means where the replica is being stored. Now let us move forward to local replication technologies. So what are the replication technologies that are followed to take a replica copy locally? Host-based, storage array-based, and network-based replications are the major technologies used for local replication. Either it may be host-based, or it may be on the storage array side, or it can be network-based replication, where the replica copy is taken over the network. Now, file system replication and LVM-based replication are examples of host-based local replication. File system, it can be based on a file system, or means you take the replica copy of the file system, or sometimes you can take the replica copy of a logical volume manager. Okay, based on the logical volume manager, you take the replica copy. That we call it as LVM-based replication. Okay, local volume manager based replication. Now, storage array-based replication can be implemented with distinct solutions, namely full volume mirroring. Either in storage-based replication, either you can perform a full volume mirroring or a pointer-based volume replication and pointer-based virtual replication. Very, very important question in this chapter. along with backup granularity, backup technologies, local replication technologies, and remote replication technologies. Out of these 4 concepts, at least 2 to 3 concepts will come in your final exam. Okay, so you should be careful in understanding these technologies. Do not get confused while presenting them in your exam, right? So in storage-based technologies, you have 3 types of storage-based technologies. Again, under that, full volume mirroring, pointer-based volume mirroring, and pointer-based virtual replication. We'll see all of these in detail. Now in host-based replication, first let us finish everything about host-based replication, host-based local replication, then we go to storage array-based local replication. Okay, in host-based local replication, LVM-based, or we can also call it as LVM-based replication, and file system snapshot are 2 common methods of host-based replication. So we can take 2 approaches under this host-based replication. So it can be a logical volume-based replication or a file system snapshot, just taking the snapshot, point-in-time snapshot of a file system. These 2 can be the types of local replication. Now, how we can understand about LVM-based replication? The LVM-based replication, in the LVM-based replication, the logical volume manager is responsible for creating and controlling the host level logical volumes. You know how the logical volumes are created, right? If we have the physical disks, out of these physical disks, you will have logical volumes created which virtually present you the physical disks, and out of these logical volumes, you will have logical volume groups. Right? All this kind of virtualization of the volumes, all this kind of virtualization of the physical disks is done by the logical volume manager software. It can be a software which organizes this entire virtualization mechanism. Okay, now in logical volume manager based replication, the logical volume manager who is responsible for this kind of virtualization is also responsible for creating and controlling the host level logical volumes. Yes, and an LVM has 3 components here. The physical volumes, you know, these are the physical volumes, what I have drawn here. These are the physical volumes. Volume groups, logical volumes grouped into volume groups, means these are the volume groups, and logical volumes. These are the intermediate level logical volumes. These are 3 components of logical volume manager. Physical disks connected into logical volumes presented as logical volume groups. These are the 3 components of logical volume manager. Now a volume group is created by grouping one or more physical volumes that we have seen right now. Now logical volumes are created within a given volume group. Now how the logical volumes are created? Logical volumes are created within a volume group. So within this volume group, you may have a logical volume. Within this volume group, you will have a logical volume, which are in turn collection of physical volumes. Now a volume group can have multiple logical volumes, that we know, right? A logical volume here can contain multiple logical volumes. Now in logical volume based replication, what will happen? Each logical block in a logical volume is mapped to 2 physical blocks on 2 different physical volumes. One contains the original copy and the other one contains the replicated copy. Understand this carefully. In LVM based replication, each logical block means the content of the file divided into blocks. That logical block in a logical volume is mapped onto 2 physical blocks. Instead of 1 physical blocks, it is mapped onto 2 physical blocks. One contains the original block and the other contains the duplicate block or the replicated block. Okay, on 2 different physical volumes. Now an application write to a logical volume is written to the 2 physical volumes by the LVM device driver. So when an application attempts to write to a logical volume, then it is actually converted into 2 physical volume writes. Okay, so each write on a logical volume will turn out to be 2 physical volume writes One maintaining the original copy and one maintaining the duplicate copy. Arbaz, are you there?
Yes, ma'am.
This task is performed device driver. This task is performed by the logical volume manager's device driver to convert a logical volume single write into two physical volume writes, one to save the original copy and one to save the duplicate or replica copy. This is also called as logical volume manager mirroring. So far in the initial chapters, we have seen how a logical volume manager groups the physical volumes into logical volume groups in order to store the data, in order to provide optimization to the data storage. Now, if you want to take replicas in this case, based on logical volume manager, then that is called as logical volume mirroring. Okay, mirror means having a duplicate copy, maintaining a duplicate copy. Now, mirrors can be split and the data contained therein can be independently accessed. Right? Mirrors can be split. They need not be saved on the same system because failure of that disk will result in losing of both the copies. So mirrors can be split and the data can be maintained therein and can be independently accessed. Now, what are the advantages of logical volume manager-based replication? The LVM-based replication technology is not dependent on a vendor-specific storage system. It depends on the operating system of LVM. Means vendor, while providing the storage infrastructure, he can't decide what should be the LVM-based replication technology. It typically LVM is part of the operating system and no additional license is required to deploy LVM mirroring. It depends on the operating system and on the exact the administrator himself can decide what should be the level of LVM based replication technology that have to be used. It is not at all vendor specific, but it is operating system independent and decided by the system administrator. And no additional licenses are required to deploy this logical volume manager mirroring. It can be done based on the requirements. Now you can see here on the host side where the logical volumes are provided. Actually, these logical volumes are mapped onto the physical disks, means this block of data. See, this shaded square represents block of the data. Now that block of the data through the logical volume will actually be stored as two copies. One on physical volume 1, which represents the original copy, and one on physical volume 2, which represents the replicated copy. This is how LVM-based replication is performed. Now, what are the limitations? Okay, we have seen what are the advantages of LVM-based replication. It provides us a mirrored copy. In case of a failure, we can easily retrieve the replica copy. But what are the limitations of LVM-based replication? Every write generated by an application translates into two writes on the disk. That is what I have told, right? The write that is generated on the logical volume, one single write, is further converted into two writes on two physical volumes. One for the original copy, that is to preserve the source copy, and the other one is to preserve the replicated copy on the target. Okay? And thus an additional button is placed on the host CPU. Whenever one write each time it is giving two write penalties, then it will be obviously a button on the host CPU itself. Now this can degrade the application performance obviously because it is translating into two writes each time a write has to be performed. Now presenting an LVM based local replica to another host is usually not possible because the replica will still be part of the volume group, which is usually accessed by one host at any given time. Now, you can't take this LVM-based local replica to another host because one logical volume, while writing the data onto two physical volumes, those two physical volumes should be part of this logical volume. So this write operation can't be even shared onto a different host also in order to reduce the overhead. That is not at all possible. Now, tracking changes to the mirrors and performing incremental resynchronization operations is also a challenge because all LVMs do not support incremental resynchronization. Remember, this incremental resynchronization is not part of all LVM softwares. Incremental resynchronization means whenever a change happens to the file or a block of data, that has to be immediately incrementally synchronized on the source as well as the target on the first physical volume group, physical volume, and on the second physical volume immediately. This is called as incremental resynchronization whenever update happens to the block of data. Now, tracking changes to the mirrors and performing incremental resynchronization is a challenge in this LVM-based replication. And if the devices are already protected by some level of RAID on the array, then the additional protection that the LVM mirroring provides is unnecessary. Correct? If you already have some mirroring techniques implemented by RAID, then this kind of LVM-based mirroring or for replication is actually not required. So this will become a redundant technique that we are implementing for taking the replication copy. So in such cases where the RAID techniques are already available to protect the data, in such cases you can omit this LVM-based replication. Now this solution does not scale to provide replicas of federated databases and applications. Now if the database is not centralized, if the database is federated onto multiple clients, in such cases, this solution is not easy to scale up. And both the replica and source are stored within the same volume group. And if the volume group altogether fails, then the source as well as the replica will be lost. That is another disadvantage. Therefore, the replica might become unavailable if there is an error in the volume group. That is what I said. If the server fails, both the source and the replica are unavailable until the server is brought back online. Until the failed server is restored, both the source as well as the replica copies will be completely unavailable because they belong to the same volume group. That is another disadvantage of LVM-based replication. So what is the only advantage? You can quickly perform the write operations because the physical volumes belong to the same logical volume group. Now there is another mechanism to take this host-based replication, that is file system snapshot. In this file system snapshot, it is a pointer-based replica that requires a fraction of the space used by the production file system. So part of the space used by the file system can be used in order to take this pointer-based replication. This snapshot can be implemented by either file system or volume manager. So this is not static, that only file system has to implement this file system snapshot or only LVM has to do this file system snapshot, means to take the replica. It can be done either by the file system or by logical volume manager. It uses the copy on first write principle to create snapshots. Remember the COFW, very, very important concept that we'll be dealing throughout the remaining part of this chapter. It uses the copy on first write principle to create the snapshots. Means whenever a first write happens, immediately copy will be performed. Means whenever an updation happens, immediately the copy will be performed. Now, when a snapshot is created, a bitmap and block map are created. See these two entities here, a bitmap and a block map are created in the metadata of the snap file system. So whenever a snapshot of the file system is taken, along with that snapshot, a bitmap and a block map are created, which are provided as the metadata of the snap of this file system. Now the bitmap is also used to keep track of blocks on the production FS after the snap creation. So what is the bitmap responsible for? What kind of data it stores? It keeps track of all the blocks that are updated on the production FS. On the production FS means on the client side. If any changes has been made to the blocks, then immediately that will be kept tracked by this bitmap entity after the snap creation. Okay, after the snap is taken, if at all any changes occurs to the file system, immediately they'll be recorded in the bitmap. And a block map, what does that do? The block map is used to indicate the exact address from which the data is to be read when the data is accessed from the SnapFS. So once a snapshot of the file system is taken, this block map will have the exact address from which the data has to be read when the data is further accessed from the snapshot of the file system that is taken. Means if the replica copy has to be accessed, where it can be accessed, what is the exact address from where the replica copy can be accessed, that is kept with the block map. Now immediately after creation of the file system snapshot, all reads from the snapshot are actually served by reading the production file system itself. Now in a copy on first write mechanism, if a write IO is issued to the production FS for the first time after the creation of a snapshot, the and the original data of production FS corresponding to that location is moved to the snap FS. So the original data of the production FS corresponding to that particular location where the updation has happened is moved to the snap file system so that the new change that is made is also reflected in the snapshot of the file system that is taken. Now then the write is allowed to the production FS. Only then the actual write will be allowed to the production FS. The bitmap and block map are updated accordingly once this write has been completed. Once this new updation has been completed to the file system. The subsequent writes to the same location do not initiate the copy on first write activity. So any other writes that happens to the same location, it will not anymore generate the copy on first write activity. Only the initial write will perform that. That is why the name copy on first write. Now to read from SnapFS, the bitmap is consulted because the bitmap will keep track of all the blocks that are recently updated. Now if the bit is 0, then the read is directed to the production FS because no changes have been recorded in the bitmap. But if the bit is 1, then block address is obtained from the block map and the data is read from that address on the SnapFS and read request from the production file system work as normal. So if any changes are made, it is recorded in the bitmap, then those changes are read first along with the file system snapshot. If no changes have been made, then only the file system snapshot will be read because no updations have taken place after the snapshot have been taken. That is how the file system snapshot works at host-based replication. Now this is how the write to production file system happens. Now when a new write has been given by the application, then you can see the production FS, the metadata are maintained on the production environment side, and you will have here some data has been updated with third file and fourth file where you have lots of other files. Now in this case, when this is being when this production file system snapshot is taken as SnapFS, it also has some metadata in the form of block map and in the form of bitmap, right? The bitmap contains all the recent updations that are made to the files, and the block map contains all the addresses from where the file system snapshot can be accessed. Now, when some updations are made to this part of the data, data C and data D, immediately they will be available on the snapshot side where it will create a block map also for those updated data. Here you can see in this case there is bit that is enabled where the updations have been made. Here data D and data C, some updations have been made. Accordingly, the bits are enabled for file 3 and file 4, right? The block addresses have been changed, and at the same time block addresses means from where, which address the file can be accessed, that has been changed, and at the same time the bitmap is also enabled to 1, indicating that a change has occurred in this file system 3 and 4. Accordingly, first, whenever the snapshot is being read, the changes are read according to what is indicated by the bitmap, along with the other data where the change has not happened. So bitmaps will help us to indicate that there are some updations made to some file systems, and those updations can be read while reading the snap of this file system when the replica copy has to be retrieved in case of a failure. Now there is another kind of local replication, that is storage array based replication. In this storage array based local replication, the array operating environment performs the local replication process. It is not the LVM, or it is not the say the client which performs the replication task. It is the storage array that performs the actual local replication. The host resources such as the CPU and memory are not used in the replication process. So the host can concentrate more on application request servicing. Okay, so the host resources in this case are not used, like CPU, memory are not used in taking the replication, in performing the replication process. Consequently, the host is not burdened by the replication operations. We are actually keeping it dedicated. The host can be dedicated only to serve the application request. It need not waste its time in performing the replication task. So all the replication responsibility can now be handed over to the storage array itself rather than to the host. Now the replica can be accessed by an alternative host for other business operations, right? So in this replication process, the required number of replica devices should be selected on the same array, means on the same storage array side, and then data should be replicated between the source replica pairs, means source where the original copy resides, target where the replica resides. Between this, the data replication mechanism should take place. Now this is how storage based local replication works. You can see this is the production host through where it uses the storage array where the original copy is stored. The read writes are performed against this original copy, and at the same time there will be business continuity host which is responsible to take only the replica copies. So that replica copy also will be maintained in the same storage array. So that on the source will serve all the production host requirements, and the replica will serve all the business continuity requirements. Means whenever a failure occurs, then the source need not be disturbed. All the restoration operations can be done from the replica that is available in the storage array. The duplicate copy that is available in the storage array can ensure the information availability to ensure business continuity. Okay, so we have divided the responsibilities between the hosts as production host and the business continuity host, where the production host can have access to the original data, and business continuity host can have access to replicated data. Now, what are the types of storage array based local replication? There are three types again under this: full volume mirroring, pointer-based full volume replication, and pointer-based virtual replication. So replica devices are also referred to here as target devices accessible by other hosts. So whenever I say source, it is the storage disk which contains the original copy. Whenever I say the target, it is the disk which contains the replicated copy. Okay, source here contains the original copy, and target here is a physical disk that contains the replicated copy. Right? This is how you understand about source and target devices. Now, what we do in full volume mirroring? In full volume mirroring, the target is attached to the source directly and established as a mirror of the source. So in full volume mirroring, you can attach the target where the replica is stored directly to the source, and it can be established as a mirror of the source, a perfect mirror copy of the source. Now the data on the source is copied to the target in order to maintain the replica copy. Now any new updates to the source are also updated on the target immediately, so that it maintains a consistent copy of the source. Now, after all the data is copied and both the source and the target contain identical data, the target can be considered as a mirror of the source, right? After all the data on the source is copied onto the target, then target itself can be considered as a mirror copy of the source. Now, while the target is attached to the source, it remains unavailable to any other host, but the production host continues to access the source. This is very important point you need to understand. While the target is kept attached to the source, it remains unavailable to other hosts, means to business continuity hosts. In this case, if both are connected, source and the target are connected, in such cases, when the replica is being taken from the source, at that time, this replica, this target will be unavailable to any other business continuity hosts. Okay. Now, after the synchronization is complete, means after all the source data is synchronized onto the target data, the target can be detached from the source and made available for other business operations. Now, once the copy is obtained, once the mirror copy of the source is obtained on the target, then the target can be made available online to be accessed by the other business continuity host for performing the business operations. Now, I'll show you on the next slide when the target is detached from the source, how actually it looks like. Now, both the source and target can be accessed. Both the source and target can be accessed for read and write operations by the production and business continuity hosts respectively once they are detached. But unless they are attached, only source will be available, target will not be available. Now, after detaching from the source, the target becomes a point-in-time copy of the source, right? And as long as the target is attached to the source, it will be taking all the replicas synchronously. But once the target is detached from the source, then that will become a point-in-time copy. That will become a snapshot till that point of time. Whatever is there in the source, that will be available in the target. Now, any changes made to the source will not be available on the target. That is why we call it as point in time. Up to that time, the source's replica copy is available on the target. Now, the PIT of a replica, the point in time copy of a replica, is determined by the time when the target is detached from the source. So, example, if the time of detachment of the target from the source is 4 p.m., then we call that copy as the PIT for the target is 4 p.m. Means the point in time copy for the target is 4 p.m. Up to 4 p.m. you have the source's replica. After that, any changes made to the source is not available on the replicated copy. Now, after detachment, changes made to both source and replica can be tracked at some predefined granularity. Now, after both are detached, any changes made to the source can be kept track by using a predetermined granularity. Means every 1 hour, you can go back to the checkpoint and recover it as a backup. And keep track of it and take it as a backup. At the same time, on the replica side also, if any changes are made to the replica by the business continuity host, still that can also be kept track by some predefined granularity. Up to this point, backup has to be taken. Up to this duration, backup can be taken like that. Now, this enables incremental resynchronization, source to target, or incremental restore, target to source. So, once some changes are made after the source and target are detached, any changes made to the source can be synchronized to the target, and any changes made to the target can be synchronized to the source. Now, when you are synchronizing the data from source to target, we call it as incremental resynchronization. And any changes made to the target, if you are synchronizing it onto the source, then we call as incremental restore. It is not a synchronization, but it is incremental restore because you are restoring the changes made to the target to the source back. That is called as incremental restore. Now, the granularity of the data change can range from 512 byte blocks to 64 KB blocks or higher. So it can be taken whenever change happens up to 512 bytes or up to 64 bytes or up to 1 GB, then at a time that source can be synchronized to the target, or at a time the target can be restored to the source. So you are creating a buffer kind of thing. You're creating a granularity where up to this much level, up to 512 bytes, the changes can be accumulated and synchronized to the target. Up to 64 kilobytes, the changes can be accumulated on the target and restored to the source. That is how you perform full volume mirroring. This will indicate how you perform full volume mirroring with source attached to the replica. In this case, source is attached to the replica in the storage array, and any changes made to the production host can be immediately reflected on the replica. But at that time, replica will not be available for to be accessed by any business continuity hosts. Right? As long as the replica is attached to the source, it is no longer accessible until it is detached from the source to the business continuity host. But you can see in the next figure, full volume mirroring with source detached from the client replica. So in this case, we have detached source from the client, so that source is available to the production host for for performing read and write operations, and replica is available to the business continuity host to perform the read and write operations. Now, any changes made to the source can be eventually synchronized to the replica by performing incremental synchronization process, and any changes made to the replica can be restored to the source by performing incremental restoration operation. Got it? Now let us see the next type of array-based replication, that is pointer-based full volume replication. In the previous case, we have seen full volume mirroring replication. Now we are going to see pointer-based full volume replication. In this case, and this is another method of array-based local replication and is pointer-based full volume replication. So similar to full volume mirroring, this technology can provide full copies of the source data on the target. So as in full volume mirroring, when the source is attached to the target, it provides full volume mirroring for us. Now, unlike full volume mirroring, what is the contrast between full volume mirroring and this pointer-based mirroring? There should be some change, right? That is why we are treating it as the second type. So unlike full volume mirroring, the target is immediately accessible by the business continuity host after the replication session is activated. So once the replication session is activated, still the target is immediately accessible to the business continuity host. It need not wait for the detachment of the target from the source. That is the advantage of pointer-based full volume replication. Therefore, data synchronization and detachment of the target is not required to access it. The target need not be detached from the source. Though the source and the target are attached to each other, still the replica copy, still the target will be available continuously for the business continuity host. So you need not perform synchronization of the updations, or you need not perform detachment of the target from the source in order to make it accessible to the business continuity host. Here, the time of replication session activation defines the PIT copy of the source, point in time copy of the source, can be defined by the time of replication session. When you invoke a replication session, that will be the point in time copy of the source. Now, pointer-based full volume replication can be activated in either copy on first access mode or full copy mode. So whenever an access is being performed, then copy on first access process can be activated, or full copy mode also the replication can be activated. Now, in either case, at the time of activation, a protection bitmap is created for all the data on the source devices. Yes, whenever some replica has to be taken, whenever the full volume replication has to be activated, then immediately a bitmap is created to indicate what all files have been changed, where the bit will be initialized, where the bit is translated to 1, and where the files are not touched, then the bitmap will be available as 0 itself. Based on that, the replication can be taken only for the updated files. And the other files where the data is not updated, they can be kept as it is. Now the protection bitmap keeps track of the changes at the source device. That is what I said. It keeps track of the source the changes that are made to the source device, and accordingly it will respond while taking the replicated copy. Now the pointers on the target are initialized to map the corresponding data blocks on the source. So the pointers that are available on the target are initialized to map the corresponding data blocks on the source where the updations have been happened. To that, the pointers will be created so that only those changes can be reflected on the replica copy once the full volume replication has been activated. Now the data is then copied from source to target based on the mode of activation, whether it may be a full volume activation or whether it may be a copy on first access activation or a full copy mode activation. Based on that, the data is copied from source to target. Now this is what happens when a copy on first access is performed while writing to the source. Means while a write operation is happening on the source, then how the actual copy on first access approach is performed. Now you can see here the production host, it is trying to write some new data. You can see here the 3 lines, horizontal lines indicates new data. And the vertical lines here indicates original data. Original updation means before the new data is written. In this case, there is original data on the source. Now new data is being written by the production host. In that case, the first step, the production host writes new data to the source. Now in the second step, original data is copied from the source to the replica. Okay, so when the production host attempts to write some new data to the source, first the source will copy the original data to the replica, means that is the target device. Okay, so this arrow indicates that original data is copied from source to the replica. Now the production host will be able to write the new data to the source, means the new data is updated on the source, right? This is how copy on first access is performed. Copy on first access means when the source is being accessed for the first time, immediately the source's previous copy will be copied onto the replica. Only after that the new data is written to the source. Now here you can see in this case when the how the copy on first access will be performed when a read is being performed from the target. From the target means the replica copy. When a business continuity host wants to read the data from the target device where the replica is available, then what happens? Read request from the business continuity host is sent to the replica copy. Then original data is copied from the source to the target because the business continuity host is attempting to access the replica copy to read some file. Immediately when that access is performed, when a first access is being performed, then copy on first access takes place. Means the source data, the original data is copied from the source to the replica. Only then the data is provided to the business host. Only then, because the source's replica is now available with the target, then that data will be, that data can be read by the business continuity host. This is called as copy on first access. When the business continuity host wants to access the replica copy to read the data from the target device, that is the replica copy, immediately the copy from the source is copied onto the replica. The original data from the source is copied onto the replica, then the replica is read by the target, so that it will have all the updated copy from the source available in the replica. Now you can see when a write operation is being performed on a target, then how copy on first access will respond. Now in this case, the business continuity host writes new data to the replica. So this host is attempting to perform a write operation on the replica, on the target device. What I said, source contains the original data, replica contains the mirrored copy, duplicate data, right? Now, when the business continuity host write some data to the replica, then original data is copied from the source to the replica first, then new data is updated on the replica. Okay, so that there will not be any incompatibility between the source and the replica after the updation. This is called as copy on first access when target write is requested by the business continuity host. Got it? This figures are very clear for us to explain what is happening whenever some write happens to a source, whenever some write happens to a target, when the data is read from the source, when the data is read from the target, how the copy on first access approach will be executed. That is shown in these figures clearly. Now the next kind of replication is pointer-based virtual replication. We have seen under storage array-based replication, full volume mirroring replication, and pointer-based full volume replication. Now we are seeing pointer-based virtual replication. In pointer-based virtual replication, at the time of replication session activation, the target contains pointers to the location of the data on the source. So whenever replication, pointer-based virtual replication has to be, that activity have to be initiated, then the target will contain pointers to all the locations of the data that is contained on the source. Okay, rather than having the duplicate copy of the entire data, it will contain the pointers that are pointing to the original data on the source. Now the target does not contain data at any time. This is the best part of this pointer-based virtual replication. The target will not contain any data. It will just contain the pointers to the data where the data is stored on the source. Therefore, the target is known as virtual replica. Actual replica means it contains the data. Virtual replica means it contains pointers to the data. Similar to pointer-based full volume replication, the target is immediately accessible after the replication session activation. Though the replication session is running, still the target will be available to the business continuity host without having to be detached from the source. Now, a protection bitmap is created for all data blocks on the source device, because it has to see whenever some updations happen to the source data, that bitmap has to be updated so that it reflects the changes made to the original copy. So the granularity of data blocks can range from 512 byte blocks to 64 kilobyte blocks or greater. Again, you can accumulate data up to 512 byte updations or 64 kilobyte updations. Only then the pointers can be repointed to the original data when some updations happen. Now, pointer-based virtual replication uses the copy on first write technology. Virtual replication uses copy on first write technology. Now, when a write is issued to the source for the first time after the replication session activation, then what will happen? The original data at that address is copied to a predefined area in the storage array. This area is generally known as save location. So whenever a write request is sent by this host, production host, then immediately the original data at that address is copied to a predefined area in the array, which is also called as saved location. Save location. Now the pointer in the target is updated to point to this data in the save location now, not the original data. Now after this, the new write is updated on the source, so that when this source write, when the new write is happening on the source, that will make the data inconsistent, because the pointer on the target side points to the source where the updation is happening. So what will happen here is, whenever some new write operation have to be performed, the old data is moved to a save location, and pointer, instead of pointing to the old data, now it points to the saved data, and at the same time, the new data can be written to the source disk. This is how pointer-based virtual replication is done. Now let us see how pointer-based virtual replication works when the host performs a write to the source disk. Now in this case, production host is writing new data to the source, where you have virtual device here. Here, instead of a target, we are referring to it as a virtual device. Why? Because it doesn't have the original duplicate data. It doesn't have the replicated copy of the original data, but it has pointers to the data that is stored on the source. Okay, so this is the virtual device, which we can treat it as a target. Now, when the production host writes new data to a source for the first time, means copy on first write. Understand, this mechanism is treated as copy on first write, COFW. Now, when the production host writes new data to a source for the first time after session activation, means when new data is reaching the source, as the next step, the original data from the source is copied to the save location, and the associated pointer is now pointing to the save location. That is what I explained, right? Now that all the data, where the data have to be modified by the new data, that data will be immediately written to the save location by the by the virtual device, which is also called as the target. That will take care that whichever data have to be modified with the new write, that data before writing the new data has to be saved to a different disk called as save location. Now, once the data is saved at the save location, then the new data is written to this disk on the source, to this location on the source, and that is indicated here in the third step. New data is updated on the source. Once this data is copied to the save location, now new data can be updated at this location, but still the pointer is not pointing to the new data. Remember, this is just copying the old data to the save location and writing the data to the previous location. Still the pointer has not been linked to that new data. Now, when a write is issued to the target for the first time after replication, now we have seen how when a write is issued to the source, what happens. Now let us see when a write is issued to the target by the business continuity host, what will happen. When a write is issued to the target for the first time after replication session activation, the data is copied from the source to the save location, and the pointer is updated to the data in the save location. That is the first step. I'll show you in the figure how it happens. Now, another copy of the original data is created in the save location before the new write is updated on the save location. Subsequent writes to the same data block on the source or target do not trigger any copy operation thereafter. That will be explained here more clearly. Now you can see the business continuity host writes new data to the target. Here new data is being written to the target device. That is where the pointers to the source data is saved, right? So when the business continuity host is attempting to write the new data to the virtual device, that is the target, as a second step, original data from the source is copied to the save location. So where it is attempting to write the data, to this part, right? So that part is immediately saved to the save location. That part is immediately transferred to the save location. And as the second part of second step, what will happen? Another copy of this data is made in the save location. Means this copy where the new data have to be written, that will be saved to the save location, and another copy of this will also be created from the source device. Okay, so you will have the original data from the source written on the save location, And you will have the new data also to be that is written on the save location. Now, the first copy of the original data is then updated with new data in the save location. So as a third step, you can see that the original, that the new data that have to be updated, first it is written to the save location, later it will be written to the source and the pointer will be reassigned. I'll explain this once again. When the business continuity host writes the new data to the target, when it attempts to write the new data to the target, what is the first step that takes place? Original data from the source is copied to the save location. So what is original data from the source? This data from the source is copied to the save location. Now, once this data is copied to the save location, as a second step, another copy of this data is made on the save location. Means the same copy is again made on the save location. After this, the first copy of the original data is then updated with new data in the save location. So the data that is being written by the business continuity host, it is first written to the save location. It is updated on the original data that is already existing, and later, as a later step, the pointer will point to the pointer in the virtual device will point to the new data that is written by the business continuity host. Now, the third type of replication, local replication, is network-based replication. So far, we have seen host-based replication. Under host-based replication, we have seen logical volume-based replication and file system snapshot. Under storage array-based replication, we have seen full volume mirroring and pointer-based full volume mirroring and pointer-based virtual replication. Now, as a third type of local replication technologies, we are seeing this network-based local replication. In network-based replication, the replication occurs at the network layer between hosts and the storage arrays themselves. So you have a protocol, right? You have a protocol stack where each layer is responsible to perform some kind of mechanism during the communication between host and the storage devices. Now, in network-based replication, the replication occurs at the network layer, the layer which is responsible for setting up the network communication between the host and the storage array. That network layer is responsible to perform the replication that communicating between the host and the storage array. Now, network-based replication combines the benefits of array-based and host-based replication. So this is a combination. All the goodness of array-based replication, storage array-based replication, and all the goodness of host-based replication can be embedded together because of this network-based replication. It combines the benefits of both the previous two replication mechanisms. By offloading replication from servers and arrays, network-based replication can work across a large number of server platforms and storage arrays, making it ideal for highly heterogeneous environments. Now, in heterogeneous environments where multiple devices that are operating with multiple operating systems, and at the same time, if you want to free the servers or the hosts and the storage arrays from this replication tasks, to clear them off from the overhead of these replication tasks, this network-based replication will be helpful. Now, continuous data protection is a technology used for network-based local and remote replication. Be it a local replication or a remote replication, this network-based replication will provide continuous data protection. Means it will ensure the data availability on the source side as well as the target side, both to the production host as well as the business continuity host. Continuous data availability, continuous data protection is provided by this network-based local replication. Now let's move on to remote replication task. Okay.
Time up.
Yeah, we don't have sufficient time. So let us take one more class to see what are the what is remote replication, what are the modes of remote replication, and remote replication technologies. Like we had local replication technologies, we also have some technologies associated with performing remote replication. That we'll see in the next class. One more class we may require to complete the syllabus. So be available for that class also. Okay, let me take attendance before concluding the class.